Horbatsch.
Horbatsch, sorry. I'm sorry. Michael is currently a postdoc at Mississippi, and before that he got his PhD from McMaster in Canada. We're very excited to have him join our group starting this fall. And today he's going to tell us about scalar tensor theory, scalar tensor gravity theory. So it's all yours.
Thank you. So I'm going to be talking today about scalar tensor gravity, which is an alternative or modified theory of gravity. It is an extension of general relativity where one has gravitational scalar degrees of freedom. I will begin by motivating scalar tensor gravity and briefly introducing it. We'll write down the action and field equations. And then I will tell you about some of the things that I've worked on in scalar tensor gravity, namely binary systems and neutron star structure. And then towards the end, I will tell you about some applications of this work, namely to binary pulsars and hopefully future gravitational wave observations by advanced ground-based detectors such as advanced LIGO. So that is going to be the rough outline. So it will be the introduction, then action and field equations, then binary systems, then neutron star structure, and finally applications being binary pulsars, and I'll just say LIGO. All right. So to start things off, essentially the idea behind scalar tensor gravity is to introduce additional scalar fields into general relativity, which can play a role in gravitational physics. And this means that they need to be sufficiently light to be interesting for astrophysics or cosmology. And there are several different reasons why one might want to consider these kinds of theories. There are many naturalness problems in fundamental theoretical physics. In other words, fine-tuning problems, and different mechanisms involving scalar fields have been suggested in order to solve some of these fine-tuning problems. And I will not go into more details there because that would just take up too much time. But even aside from the fine-tuning problems, it is interesting, just from the point of view of classical gravitational physics, to consider theories of gravity different from general relativity. And by studying them, you can learn more about relativistic gravity and learn more about what is special to general relativity versus what is the generic feature of relativistic gravity. And that is another reason why it is interesting to consider any kind of alternative theory, not just scalar tensor gravity. So with these brief introductory remarks out of the way, I will dive into point 2 here, the action and field equations for scalar tensor gravity. And instead of just pulling an action out of a hat, I want to construct it from some guiding principles. So if you want to construct an action, the first thing you need is a field content. So the field content that we are going to use is going to be a metric tensor. So I will write that as G mu nu, as usual, as well as some new scalar fields that we are going to introduce, which I will call phi. And I'm going to consider the possibility of more than one scalar field. So I'm going to have an index on this phi, which I will write upstairs, and I will use Latin letters for indices on the scalar fields and Greek letters for space-time indices. So I want to build an action that is a functional of G mu nu and the phi a's. And in general, this can be a very complicated thing. But one way in order to simplify things is to expand the action in numbers of space-time derivatives and work to just the first few leading orders. So if we do that, well, and additionally, we want to impose some symmetries. So the usual symmetries that we impose in general relativity is space-time diffeomorphism invariance. Now, we're also going to want to impose some kind of symmetry on the scalar space. So before I actually write down any equations, it might be useful to draw a geometric picture to get some geometric idea about what kind of objects we're dealing with here. So we're going to have a space-time manifold, which I'm going to call M. And then we're going to have a so-called target space manifold, which is an internal scalar space, so to speak. And I'm going to call that manifold T. So M, being the usual space-time manifold, is 4-dimensional and Lorentzian. And G mu nu is the Lorentzian metric on it, the space-time metric. Now, this internal manifold T, this target space manifold, it is going to be n-dimensional, where capital N is the number of scalar fields. So A here, the index, runs from 1 to n. Now, for now, I will not assume any other structures. I will just take T to be an n-dimensional manifold. Then the scalar field can be thought of geometrically as just a single function, phi, which maps the spacetime manifold into the target space manifold. And once you choose coordinate charts for both manifolds, you have the usual objects with the indices that I've written up here. So using these fields, we want to construct an action which is invariant under spacetime diffeomorphisms, and also we want any results to be invariant under the choice of coordinates on this internal manifold. So we're also going to demand that the action is invariant under target space diffeomorphisms. So with these constraints, let us just write down the most general action given these symmetries and given that we are working to leading order in this derivative expansion of the action. So what can we write down? So the action, as a functional of these two fields, is going to be an integral over space-time and at zeroth order in the derivative expansion. In other words, if you just write down terms that have no space-time derivatives at all, well, in GR you can only write down one thing, which is the cosmological constant. But here, because we have the scalar fields, we can have some scalar potential, v of phi. And geometrically, v is a function which maps target space to the real line. Now, at first order in the derivative expansion, you do not get anything because you cannot get the indices to contract to give you a Lorentz scalar. So the next non-trivial terms you get are at second order. And if you simplify things using integration by parts and dropping boundary terms, then essentially all the terms that you can write down boil down to two different terms. The first kind of term you can get is the one similar to what you get in pure GR. And it is basically the only geometric invariant, or the only geometric scalar that you can build out of the metric, which has two derivatives acting on the metric, which is the Ricci scalar. But we can multiply it by some arbitrary function of the scalar fields. So when I write a function of phi, I mean a function of all of these coordinates of phi. So you get the Ricci scalar r built out of the metric times some function which I will call capital F of phi. And the other kind of term you can write down is when both derivatives act on the scalar fields. And that will basically be a kinetic term for the scalar fields. And that term has, the most general form for that term is as follows. So we have one derivative, so partial mu acting on phi a, partial nu acting on phi b. And now we just need to contract the indices. And the only objects we can use to contract the Lorentz indices down here is the spacetime metric. But then we need some object to contract these internal scalar indices. And I'm going to call that object gamma sub AB. It needs to have two indices downstairs. And generically, it can be a function of the scalar field as well. Now, if you want this theory to carry only positive energy excitations, in other words, have no ghosts, you're going to need to impose the requirement that F be positive, and this gamma AB be a positive definite bilinear form. And that kind of object is precisely a Riemannian manifold on this internal space, on this internal target space. So basically, if we want to construct an action that leads to a well-defined gravitational theory, we're going to need some more structure on this internal space. We need to demand that it be a Riemannian manifold. So Riemannian manifold with Riemannian metric gamma AB. So then this will be a symmetric positive definite tensor on the target space manifold. Now, in principle, I could keep going and write down more complicated terms with more than two space-time derivatives. But for our purposes, I will cut off the expansion at this point. And one way to justify this kind of expansion is to argue from quantum field theory and effective field theory that terms with higher numbers of space-time derivatives are going to be suppressed by large mass scales. However, it is important to keep in mind that these higher terms can be highly nonlinear and lead to important strong deviations from just this leading order term that I wrote down. So so it is easy and to make this argument that this is the most general thing at this order, but it is still worth considering theories which have complicated higher order terms, and they can lead to a lot of interesting structure. One example of that is the Weinstein mechanism, but that will be beyond the scope of my talk. For the purposes of my talk, I will restrict attention to this class of theories where we cut things off at the second order in the derivative expansion. And I should point out that this theory that I wrote down, well, actually, before I say that, let me say one more thing. So we can make a further simplification. So first of all, what I wrote down is just the gravitational action in vacuum. But of course, to this, you need to add some matter action, which I will call as mat. And I will not be concerned with the precise form of this matter action at this point. But I will just say that it is in general, some functional of the metric, the scalar fields, and the other matter fields in your theory. And I will just collectively denote all these other matter fields by capital psi. Now, one thing we can do to simplify things is carry out field redefinitions. And one field redefinition we can make is define a new metric called G star mu nu to be some function of phi, which I will call G of phi times G mu nu. So at the end of the day, any predictions that we make using this theory, which relate physically observable quantities to other physically observable quantities, any of these predictions have to be independent of our choices of fields, and they have to be invariant under field redefinitions. So that is why we have this freedom to redefine fields, to simplify things. And basically, if we choose G correctly, and write the action in terms of this G star metric rather than the G metric, then what we can do is basically kill this f of I term and replace it by unity. But that is when you have a star down here, a star here. So all quantities are now computed, and a star here. So all quantities are now computed using this G star metric rather than the G metric. And this G star metric is sometimes called the Einstein frame metric, whereas the G metric is usually called the Jordan frame metric. So now once I write things in the Einstein frame, this action that you see should be something quite familiar. Basically, this is just a nonlinear sigma model minimally coupled to gravity. That is all it is. So now that I wrote down the action, I will just briefly say a few things about the field equations. Yes?
So the redefinition of the metric you wrote down,
Yes?
I can still consider yet another redefinition where I add two derivatives, so del nu phi, add to that.
So you mean adding something like plus h of phi di mu phi a di nu phi b, and I guess you need ab here.
So does it do any further simplification, or? That's the most general field redefinition, which is two derivatives.
Right. Well, I mean, in principle, you could also start adding things like r here. So that would be 4 derivatives. But if you had only r but no derivatives there, I mean, you could try adding something like r g mu nu. Like in general, I think you could have a function of r here too, and there would be 2 derivatives. I mean, so this is not something I've thought about before. The most general, field definition, up to 2 derivatives, and that is an interesting question. Can you simplify things even further? I'm not sure, but my gut feeling is that it will not simplify things even further. But that is just my gut feeling. But maybe we can discuss later.
If you use field definitions with 2 derivatives, wouldn't you pass that term imply that you get terms with 4 derivatives in the action?
Yes, I think you're right that if you try to simplify things using this kind of term, then the resulting action and field equations will a priori be higher than second order, even though it is just this choice of fields that makes it look like it is a higher order theory. It really is just a second order theory at the level of the field equations. So that is probably why people do not consider this kind of redefinition. So that probably is a better answer to your question. Right. That if once you start introducing derivatives here, then you get a theory whose equations of motion will have more than 2 derivatives. So that, I guess, is usually why we restrict to just these kinds of field redefinitions. Okay, so given this action here, with that simplification going to the Einstein frame, I will just briefly write down the field equations. So for the tensor field equation, which you obtain by varying the action with respect to the metric, you basically get the following. So we will get the usual Einstein tensor. And in GR, you just have the energy momentum tensor of matter, so T mu nu of matter, on the right-hand side. So I'm just writing the schematic form. I'm not going to worry about all the constants and all the signs and everything. And basically, you just get a new contribution here, which is going to be the energy momentum associated with the scalar fields, which I'm just going to call T mu nu sub phi. And I will not bother writing out the precise form of that. It is something very standard. Quadratic in derivatives of the scalar field. Now, for the scalar field equation, if we were to have just a single scalar field, then the equation would basically read the following. So we would have the wave operator acting on a single scalar field phi, and on the right-hand side, you basically get 2 kinds of sources. One source comes from the potential, so that will give you a derivative of the potential. And the other kind of source you get from the matter, which I will write as just explicitly as the functional derivative of the matter action with respect to the scalar. Now, once we have more than one scalar field, there is one obvious thing you do is you just put indices everywhere. So here we have phi a. Now, the derivative here is just going to be a partial derivative, partial v, partial phi a, and here we have an index. However, there is one more change that is needed. The right-hand side transforms as a vector under target space diffeomorphisms. However, the left-hand side does not, because this is a second-order differential operator. So what we need to do is we need to construct a target space covariant second-order differential operator. So basically, we need to replace this familiar box with something that I will just call a diamond acting on phi a. And basically, just by requiring this left-hand side to transform covariantly under target space diffeomorphisms, you can basically determine what this diamond operator has to be. And what you find is that diamond acting on phi a is basically going to be box acting on phi a plus a correction term that involves the Christoffel symbols of that target space metric gamma AB. And the correction term basically looks like this. So we have the Christoffel symbol of gamma AB, which I'm going to call gamma ABC here, which is a function of phi. And then these 2 bottom indices get contracted with derivatives of the scalar. So partial mu, phi b, partial nu, phi c, contracted with the spacetime metric g mu nu. And this resulting object once you add this correction term, is going to transform like a target space vector.
So you get that by varying the action.
Yes, you get this, and there are coefficients and signs that I might have gotten wrong here, but you get this kind of structure by varying the action. Yes. All right, so this was point number 2 here, the action and the field equations. So now I will go on to consider binary systems. And I want to consider binary systems, first of all, of objects that themselves can have very strong internal gravity. So it could be black holes, could be neutron stars. And I also want to consider the regime where the two objects are sufficiently separated so that postNewtonian methods can be used. So in a nutshell, I want to consider some body which I will call 1, a body which I will call 2, and they each will have some characteristic size which I will call r sub 1 and r sub 2, and they will have some separation that I will call d, and they will have some relative orbital velocity which I will call v. Now in general, if say d is comparable to r1 or r2, then you cannot really use analytical methods and you need to solve this numerically. But I will be only interested in the regime where r1 and 2 are much less than d. In other words, the system is widely separated. And if it is gravitationally bound, it will follow from this assumption that v over c, if we put in all the units, is much less than unity. So basically, the postNewtonian analysis is applicable. And I will also write the masses here as m1 and m2. And in order to come to this conclusion, I need to make one other assumption, which is that m1 is comparable in order of magnitude to m2. If this were not the case, then I can use different approximation methods. Namely, I can work with the background geometry of the heavier object and then perturb it and look at the motion of the lighter object in that background. But that is not what we are going to be doing. So we consider the masses to be comparable, and that is what will then justify the postNewtonian treatment. All right, so we want to specialize these general field equations that I wrote down to a binary system. So I should also point out that the applications we have in mind here, well, as I said already, are binary pulsars, where this is applicable. In binary pulsars, v over c is around 10 to the minus 3 at most, I think, if I remember correctly. Now for LIGO, this need not be true, but it is still useful to do this kind of analysis. And I will not go into the details of that. All right, so I want to specialize those field equations of scalar tensor gravity to those of a binary system. Now, and I'm working in this limit that v over c is much less than 1. And then it is useful to use an effective point particle description, where I basically describe these bodies as just point particles, and I have some effective Lagrangian, which encodes all information about the internal structure and strong self-gravity, or possibly strong self-gravity, of these bodies. So basically up there, I just wrote S matter as some arbitrary functional and let it be anything. But now I will tell you what kind of functional we need to take if we want to describe a binary system in this point particle limit. So basically, you end up using something like this. So S matter is going to be, first of all, a sum over all the bodies. So I will just write this generally for an n-body system, although ultimately I will be interested in applications to just binary systems of 2 bodies. Now for each body, we have an integral over the world line of the body, which I will call gamma sub a. So a is going to be an index that labels the bodies. And then we're going to integrate with respect to the invariant arc length along that world line, and I'm going to call that ds sub a. And then in general, here we're going to have some kind of functional of the fields of g mu nu and phi, which is going to be like an effective Lagrangian for that body, for the 8th body. And just like we used the derivative expansion when constructing the action for the gravitational sector, we are going to also be using the same derivative expansion for this matter action. So the leading order term, which has zero derivatives, zero spacetime derivatives, well, in GR it would just be the mass of the particle, but here the mass can be a function of the scalars. And then you get higher order corrections, which I will not even write down because otherwise I will probably run out of time, but they basically contain derivatives of phi times other functions of phi. So this kind of formal analysis shows you that the mass of a body is going to depend somehow on the scalar environment within which it is embedded. And if you think about that from the point of view of solving the stellar structure problem, in other words, solving the field equations in the interior of a neutron star or a black hole, then this intuitively makes sense, because in order to solve those field equations inside a body, you need to impose some boundary conditions of what happens to the scalar field when you go far away. And a priori, that structure of a neutron star will depend on what is the value of the scalar field far away. And this dependence is exactly what this function here is encoding, how the mass of the object depends on the external scalar environment in which that object is embedded. All right, so that is the matter action that we are going to be using. And of course, if you want to calculate this mass function in principle, if you want to calculate this mass function in practice, then you will need to make some assumptions about how the scalar couples to matter at the particle level. And you'll also need to make some assumptions about the equation of state of the neutron star, if you're interested in neutron stars. And that will be discussed in the next point, in the next part of the talk. But for now, I'm just going to assume that these mass functions are just given to us. And in terms of those mass functions, I want to work out the orbital dynamics. So that is what we're going to do now. So describing the orbital dynamics of a binary system is a long story, and I'm not going to give all the details, but I will just give some highlights. So at the Newtonian level, the dynamics of the two-body problem is relatively simple. Basically, you just have an ellipse. The shape of the orbit is an ellipse, which does not precess, and you can write down a relatively simple equation which will describe the motion in time for you. You cannot get it explicitly as, x or y is a function of time, but you can define it implicitly through this so-called Kepler's equation. But once we go to high orders in this v over c expansion, so we are going to basically be expanding in powers of v over c. That is what the postNewtonian expansion is, really. And once you include higher order v over c corrections, then this ellipse is going to start to precess. And the other thing that is going to happen, if you go to at least, well, let me not worry about the details, but if you go to sufficiently high order in v over c, then also gravitational radiation is going to be emitted, and this ellipse is going to start shrinking. And the system will give off gravitational radiation. And these things can be observed in binary pulsars through timing of these pulses that arrive to us, to the radio telescopes on Earth. So it is of great theoretical interest to work out the predictions for the precession rate and the rate of shrinking of the orbit. And that can be done, and that has been worked out. So I should point out that all of this that I'm describing, this is not my work. This is work that has been done by many, many people, and I do not have time to cite all the people who have done this. But all this work started in the late 1970s, soon after Hulse-Taylor discovered that famous first binary pulsar. So towards the end, I will talk more about what I more specifically have worked on. But for now, this is basically just a review of things that were done in the late 70s up to the 90s. So basically, predictions for these orbital dynamics have been worked out. And I'm not going to give complicated formulas for the precession rate and radiation rate and so on, but I'll just describe what kind of quantities these things depend on. So first of all, in GR, well, let me just set up some notation. So I'm going to call the orbital period P, and I'm going to call the angle of the periastron omega. So then you make predictions for p dot, dots denoting time derivatives, and omega dot. And in GR, these things are just functions of the two masses of the objects. So I should say that this is to leading post-Newtonian order. So basically, to the leading non-trivial term here has the following dependence. It just depends on the masses, and it also depends on the orbital parameters. So it will depend on the energy of the orbit and the angular momentum of the orbit. And same for this omega dot. And if you go to sufficiently high post-Newtonian orders, then you will also start picking up dependence on the internal structure of the objects, such as the quadrupole moment or the moment of inertia. Well, no, not the moment of inertia, but the quadrupole moment of both bodies. But to leading post-Newtonian order, the only parameters that these predictions depend on are the masses. And this is in general relativity. Now, in scalar tensor gravity, things get a lot more complicated. And I will just briefly explain what kind of new parameters enter into here and why. So first of all, when you're doing a post-Newtonian expansion, one of the things that you do there is that you start with some background spacetime, which is Minkowski, and you perturb around it. So you write the spacetime metric as g mu nu, as eta mu nu, the flat Minkowski metric, plus some perturbation h mu nu, which is taken to be small, and you work perturbatively in h mu nu. And similarly for the scalar fields, you write the phi a as phi infinity dA, some constant background value that I will call phi infinity, plus some small perturbations, which I will call psi a. Now, these kinds of expansions get plugged into the field equations. And there's a long story about working this out, working out these predictions. But I just want to show that, or emphasize that when you plug something like this, if you plug this expansion for phi into the matter action, then you basically get the mass function evaluated at the background value plus some correction. So if you Taylor expand that, you will pick up not just the mass, which we define to be the mass function evaluated at the background value, but if you go to sufficiently high post-Newtonian orders, you will pick up derivatives of this mass function, which basically tells you how sensitive the star is to changes in the scalar background in which it is embedded. So basically, whereas we had this simple dependence in GR and scalar tensor gravity, we also get here dependence on M1 prime, M2 prime, and depending on how far you go in the post-Newtonian expansion, you get higher and higher derivatives. Now remember that in the scalar field equation, we had terms like this Christoffel symbol here. And again, here you would plug in that phi is phi infinity plus a small correction. So basically what that means is that you will also get dependence on the geometry of the target space metric. So basically, if you go to sufficiently high post-Newtonian orders, you will also get dependence on things like the Riemann curvature tensor of the target space geometry. And if you go even higher, you would get derivatives, covariant derivatives of the Riemann tensor, ABCD. And, well, so I wrote M1 prime and M2 prime, but you take derivatives with respect to many fields, so I should really use some different notation. It is convenient and standard to define these sensitivities, these derivatives of the mass function as alpha. So I will call alpha sub a to be the derivative of this mass function. And this is all for a body, capital A. So capital A is the label for the body, and little a is the internal scalar index. So basically, the derivative of this mass function is this so-called sensitivity, alpha A. So this will depend on the masses as well as these first sensitivities. So alpha A, or alpha 1 for the first body A, and alpha 2 A for the second body. And then if you go to sufficiently high orders, you need second derivatives, which will have two indices, and it gets more complicated. So you can get terms. So basically, you can get all sorts of terms a priori where you, contract these sensitivities or contract them with the Riemann tensor. And they will all influence how this orbit shrinks or precesses, or other properties of the orbit that can be observed. So now so again, I will not write down the complicated formulas, but I just want to illustrate what kind of behavior you get. So one thing that is quite standard in general relativity is that gravitational wave emission is quadrupolar, and you do not get any monopole or dipole radiation in general relativity, because you have this spin-2 tensor field. But since we've introduced a whole bunch of spin-0 fields, we now can get monopole and dipole radiation. And basically, well, because this is a binary system, and the total scalar charge is conserved, we will not get any monopole radiation to leading post-Newtonian order, but we will get dipole radiation. And basically, the strength of that dipole radiation, so I will call F dipole for the power radiated from the dipole modes, or the dipole mode, and basically that is going to be proportional to the dipole moment squared, or the scalar dipole moment squared of the system, which is basically going to be the difference of these sensitivities, these alphas. So one way to interpret these alphas is as scalar charges. And maybe I should just write down a formula to make it more intuitive. So basically, if you study the behavior of the scalar fields in the vicinity of one of these stars, then you basically get the following behavior. So as is well known, the TT component of the metric is going to go like -1, the flat Minkowski value, plus 2gm over RC squared, plus higher order terms. And if you do the analysis for the scalar fields and their asymptotic behavior, so this is just in the vicinity of one of these stars. So this might be confusing notation, because earlier the metric referred to the metric of the entire space-time, but this is now just for in the vicinity of body A. So I will use a superscript A. And then this mass here, that is m sub A, the mass of the first, or of one of the bodies. And then if you look at the scalar fields, you basically get this phi infinity background value plus 2g m sub A times alpha sub A over RC squared. So this alpha, it basically tells you how strongly the star as a whole couples to the scalar field. And this m times alpha can be called the scalar charge of the star. Oh, and there's an A index up here. So it is kind of intuitive that the dipole radiation is going to depend on the dipole moment of the system as a whole squared. So that is what I was going to write here, that the power radiated from the dipole radiation goes like alpha 1 minus alpha 2 squared, which means that, well, you arrange with the A's, then alpha 1b minus alpha 2b, contracted with the target space metric, so gamma AB, well, evaluated at the background value, of course. So this is the leading order. This is the leading order radiated power, leading post-Newtonian order. And this is already a huge change from general relativity if you can get the difference of the A's to be large. And then just as an example of a higher order correction that comes way later in the post-Newtonian expansion, you can get a term where you get RABCD, the Riemann tensor of the target space geometry, contracted with alpha 1, alpha 1, alpha 2, alpha 2. And there is only one unique way to contract these indices to get something that does not vanish. And basically, you get an A and C on the first one, and a B and D on the second one. And it is also interesting to note that when the scalar charges are equal as target space vectors, then both of these terms actually vanish. Which is, again, quite intuitive, because you do not get dipole radiation if the dipole moment of the system vanishes. Now I will make, well, actually, maybe I will make one more comment now. So these leading order terms have been calculated back in 1992 by de Moore and Esposito-Ferez, and one of the projects that I'm currently working on is to calculate these higher order corrections and in particular, calculate the leading order dependence on the target space curvature of these fluxes. And then you get similar formulas, involving the alphas, but contracted differently for things like the precession rate and other observables. Now I will point out one other interesting thing, or one other interesting structure that can arise in the fluxes. So one thing that I should have said earlier is that this structure, and actually this whole analysis for binary systems, that was first done for massless scalars, which means that the scalar potential that I wrote somewhere way up there, the V of I, that is taken to vanish. And you can ask the question, well, what about scalars that are not massless, but are still sufficiently light to be relevant for astrophysics or cosmology, well, or these binary systems, which is what we're interested in here. And basically, I will just explain on intuitive grounds what happens. So if these scalar particles, so for simplicity, let us just consider one scalar particle now. So if you have a scalar particle phi of mass m sub phi, then the rest energy of that particle is just going to be m sub phi times c squared. Now, if you have an orbit of two neutron stars or black holes or some other objects, which has a frequency, orbital frequency omega, I'll call that omega orbital, then loosely speaking, the energy radiated by such an oscillator is h bar omega. So if you want there to be scalar radiation, the energy radiated by the oscillator has to exceed the rest energy for the scalar particles, otherwise they cannot be created by the oscillator. And indeed, if you work out all the details and work with not a massless propagator, but a massive propagator, then indeed, if you calculate these fluxes, you will find that they contain step functions involving h bar omega orbital minus scalar mass times c squared. So basically, the scalar radiation from these systems gets shut off if the scalar gets too heavy. And this potentially is very interesting and could be a smoking gun of a massive scalar if we were to observe a binary system, either through binary pulsars or through something like LIGO, where radiation, or where a certain mode of scalar radiation all of a sudden shuts off if the orbital frequency were to cross this threshold. And then I should also say that this was first derived in the 1990s by Will and Scalar for circular orbits, and one of the things that I'm involved with is generalizing this both to elliptic orbits and to the case where you have multiple scalars, where you would have some second derivative matrix of the potential that needs to be diagonalized. So I think that this is all I want to say about binary systems and dynamics of binary systems. So the takeaway message is that introducing these scalars can radically change the dynamics of binary systems. You can get much stronger radiation than in GR because it happens at lower order, at dipolar order instead of quadrupolar order. And you can get these thresholds, these cutoffs for the frequency of the orbit. But now there is still the issue of, or there is still the question, what are these alphas? How do you calculate them? And are they going to be sufficiently large? Or is this difference going to be sufficiently large to give you something interesting? So that is the topic that I will turn to next. So we are basically done with this. And now I will tell you briefly a few things about neutron star structure, which basically is the problem of how do you calculate these alphas? And remember, these alphas basically come by differentiating this mass function. So given some model of the neutron star, and given some assumptions about how the scalars couple to matter, the matter out of which the neutron star is built, at the particle level, given these assumptions and given some choices there, how do we calculate this mass function? And basically, what you have to do is solve the field equations in the interior of one of these neutron stars. Maybe I will do this on the other board here. So basically, now we are interested in solving the field equations that I wrote there earlier. I will not repeat them. We're interested in solving them in the interior of a neutron star. And in particular, we're interested in solutions where these alphas are large, or say of order unity, where you get strong deviations from GR. So in the limit that these alphas go to 0, or in other words, in the limit that these mass functions are independent of phi, then the scalar field profile will basically turn off, and you just recover GR. Right. So first of all, we need some assumptions about how the scalars couple to matter at the particle level. So that is what I called S-matter, the matter action earlier. And in general, it can be some functional. So in general, it is a functional of the metric, of the scalar fields, and of your matter fields. Now we want to restrict this and make some concrete choice for the matter action. And we're going to do this quite phenomenologically. And we're just going to say that we want to incorporate the weak equivalence principle, which means that matter couples to just a single metric. So basically, we are going to require that, or one simple way to do that is to require that this matter action is not a functional independently of g mu nu and phi, but that it only depends on a certain combination of the g mu nu and the phi. So we are going to say that it cannot depend independently on both, but that it can only depend on g mu nu multiplied conformally by some function of the scalar fields, which I will call a of phi, or it is conventional to actually use a squared here. So a is the conformal factor, but because this is a rank 2 tensor, we have the a squared. And this type of coupling is usually called a Brons-Dicke type coupling. And these kinds of couplings were first considered back in the 1960s by Brons and Dicke, which is usually considered the birth of scalar tensor gravity, although it really goes back much further. But I do not have time to go into that history here. So if you make this assumption, then in the field equations, the sources on the right-hand side are no longer going to be independent, but basically in the scalar field equation, the source, or I should use diamond, so diamond phi a equals, so we have the term from the potential, partial v, partial phi a, and the source is no longer going to be independent of the source in the tensor equation, but you're just going to get the trace of the energy momentum tensor of the matter fields, so T matter, times the logarithmic derivative of this coupling function. So that'll be partial log a of phi, partial phi a. And this function here, which appears in your field equations, it is useful to call it alpha with an index a of phi. So now, we no longer have an arbitrary functional of g mu nu and phi that needs to be specified if we want to say how the scalar couples to matter. But now we just need to specify a function on target space, or a vector field on target space, in order to specify how the scalars couple to matter. And we're just going to, well, first of all, the simplest thing you can do is take a constant. So we can take, alpha star sub a, and in fact, this is the theory that Brons and Dicke considered, when this alpha function is just a constant. And then you can imagine choosing different kinds of functions, but the simplest thing you can do is just Taylor expand this function. So that will be some, say, beta star, or it'll be convenient to write these indices downstairs. So alpha lower a, then you'll get some beta ab times, hold on. Yes, that's right. Beta ab contracted with phi b, and then you can keep on going. And the kinds of theories that people have considered in the literature in great detail are those with alpha and beta non-zero, but all higher order terms dropped. So that is just one simple assumption you can make to make a concrete choice about how the scalars couple to matter. And this kind of model with the beta non-zero is sometimes called a quasi-Bronsdicki model or a quadratic model. So they call it quadratic because if you look at capital A, then you have to integrate once. So in the capital A, beta will multiply phi squared and not just phi. Now, one reason this quadratic model is interesting is because people found that there is a way to get very interesting solutions for neutron stars which differ strongly from the solutions of general relativity. Or in terms of this notation I introduced here, well, first of all, I should say that if you just work with the alpha and throw out the beta, then all the neutron star solutions are going to be close to GR solutions, and all deviations are going to be of order alpha. And solar system constraints force alpha to be 10 to the minus 3 or something like that. So that basically shows you that if you just consider the classic Bronsdicki model with only the alpha and not the beta, then you really cannot get interesting physics in neutron stars. However, if you add the betas, then what you find is that these alphas I defined earlier, which quantify how much your solutions differ from GR, so remember, they're basically dimensionless, and they tell you how much the scalar field profile deviates from GR, loosely speaking. And it was found that in theories with a single scalar, so with just a single phi, where, well, the beta matrix is then just a single number beta, it was found that if beta is less than approximately minus 4, then you get a phase transition in neutron stars, and it was called that they scalarize, so to speak. And, well, to explain that, I should first say that if you consider non-relativistic stars in non-relativistic neutrons, well, no, that makes no sense. Well, just non-relativistic stars or non-relativistic perfect fluids in these kinds of models, then you can show on very general grounds that this parameter alpha A that I was talking about earlier, this alpha A, is just going to be equal to approximately this alpha function evaluated at the background in which the neutron star is embedded. So that basically tells you that if you work with non-relativistic stars, you cannot get interesting effects. You cannot get strong deviations from GR. And the interesting thing that people found is that if beta is less than minus 4, you get this phase transition where even if, okay, so I should say that this equality is for non-relativistic objects only, and it basically follows from a postNewtonian expansion. But if you have relativistic objects, and if you have beta goes to minus 4, or less than minus 4, then you can have this phase transition that even if alpha A of phi infinity, even if this coupling function, evaluated at the background, even if that goes to 0, in other words, even if the scalar decouples from matter far away from the neutron star, the coupling of the neutron star as a whole to the scalar field can still be very large. In fact, it can be of order unity. And this is very interesting because it implies that in these kinds of models, in these quasi-Bronsdicki or generalized Bronsdicki models, you can get orbital dynamics of neutron stars or of binary pulsars which deviates from general relativistic orbital dynamics by order of unity. So that is why these kinds of models received a lot of attention over the years. So basically, ultimately, what we're interested in doing is confronting these scalar tensor theories with observational data, like binary pulsar timing data, or hopefully in the future, data from advanced LIGO and other gravitational wave detectors. And basically, in the case of a single massless scalar, people have worked out, this was mostly by Demur and Esposito Fares, they have worked out the kinds of constraints that you can get on this beta parameter from binary pulsar timing. And basically, the results can be summarized by a simple theory space exclusion plot, which I will draw roughly right now. So on one axis, you're going to have phi infinity. Well, actually, let me do it differently. So first of all, they're considering a single scalar. So they're basically working, and they're making this assumption about the scalar matter coupling. So they're going to have one constant alpha star here, and just a constant beta star here times phi. So the parameters of the theory are two-dimensionless numbers, alpha star and beta star, which are going to be on the axes of this theory space exclusion plot. So here is going to be alpha star, and here is going to be beta star. Now, solar system tests alone will constrain just alpha star and will not constrain beta star at all. And they will basically give you a horizontal line like this, whose value is going to be about 10 to the minus 3. So this is from things like observing the perihelion precession of Mercury. And remember, for that, you don't need this fancy formalism, because in the solar system, gravitational fields are weak everywhere. So you can use a very simple postNewtonian treatment. This fancy treatment that I described here is a lot more complicated, because the stars can have internal structure and strong self-gravity. So this is from a very simple analysis compared to what I was just describing. And and this best bound actually comes not from the precession of the perihelion of Mercury, but rather from timing of radio signals sent between Earth and this satellite called Cassini, which was near Saturn at the time that this experiment was done. So this is one of the constraints you get from this Cassini experiment. And then the kind of, just to make it clear, what this constraint is saying is that these theories up here are forbidden, the theories down here are allowed, the origin here is GR. And I'm only drawing half of a plane because the theory has a symmetry where, if you invert the sign of alpha or the sign of the scalar field, you basically end up with the same thing. And basically, the kind of constraints you get now from binary pulsars are much different and much more interesting. So if here's minus 4, the critical value of beta at which this phase transition can kick in, then basically, once these start scalarize, they start changing the orbital dynamics so much that the results are inconsistent with the binary pulsar timing. So basically, you get a curve which excludes theories where beta is much less than minus 4. So the curves can look something like this. And then here it can go up or down depending on what kind of binary system it is. And I do not have time to go into those details. But basically, so everything to the left and above of this curve is ruled out, and everything under it, and under this line from the solar system is allowed. So these kinds of constraints have been worked out for these theories with a single scalar, with this kind of quasi-Bronsdicki coupling, and also the assumption here is that the mass of the scalar is equal to 0. And one of the projects that I'm currently involved with is to generalize this story to the case of multiple scalar fields and or the case of scalar fields with a non-zero mass. And I'm pretty much out of time, so I will just say very briefly one interesting thing that can happen in the case of multiple scalars that cannot happen with a single scalar, and that is related to this scalarization transition. So as I just mentioned, this theory with a single scalar has a symmetry of phi going to minus phi, which is a discrete Z2 symmetry. And that is a symmetry of the action in the field equations. However, it is not going to be a symmetry of a scalarized solution. So what happens here is that this discrete Z2 symmetry gets spontaneously broken. Now, if you have more than one scalar, then your theory can have a continuous symmetry, and then scalarization in this multi-field context is going to, or it can potentially spontaneously break a continuous symmetry. And that gives you much richer phenomenology than in this single scalar case. And the kind of model we're considering as a first step in this is a model with two real scalar fields written as a single complex scalar field, which has a U1 symmetry at the level of the action in the field equations, but this U1 symmetry gets spontaneously broken by the scalarized solutions. And working out the phenomenology of this is something that I'm currently working on. It is work in progress. And we do not yet have any final results, but it is looking to be very interesting. So I think that summarizes what I wanted to say, and also I'm out of time. So the takeaway message here is that introducing scalars can change gravitational dynamics of binary systems in very interesting ways. And this is very relevant for astrophysics because we can confront these theories with binary pulsar timing, and hopefully in the future with advanced LIGO and other gravitational wave observations as well. And with that, I would like to conclude. So thank you. So you said with in mind the Higgs?
You were saying your scalar fields phi are sort of functions, or the masses are functions of these fields. To me, it seems natural to maybe later on consider an SU2 doublet, which could be thought of as the Higgs.
Well, so one could certainly consider an SU2 doublet if you want a richer phenomenology and more coupling parameters to play with. But it is not really natural to consider this as the Higgs in this context, because the Higgs is way too heavy to mediate a force that is going to be observable over macroscopic distances. So the Higgs's mass is in the order of 100 GeV, but you need something, if you want something that will show up in binary pulsars, you need something on the order of 10 to the minus 18 eV. So we're talking completely different scales here. So the kinds of scalar fields I have in mind, these are not the Higgs. These are some other hypothetical scalar particles, like axions.
I actually have a question.
Mm-hmm.
So you talked about this target space,
Mm-hmm.
and especially showed that the power radiated, the dipole power radiated, depends on the curvature on this.
Mm-hmm.
Right? So there is, and before that you introduced the gamma, the main trick on this target space.
Yes.
So how do you so do you write down a completely general ansatz, just imposing that it has a positive definite metric, or do you make more restrictions because it would eventually come in, right?
Okay, good question. And that depends on what you want to do. So if you just want to work out the power radiated from a binary system in this postNewtonian framework, then you can do this without making any assumptions about the geometry of the target space. So basically, at the leading order, you just get the Riemann tensor evaluated at this point about which you're perturbing. And then if you go to higher orders, you pick up higher derivatives of the Riemann tensor. And basically, that as you go to higher postNewtonian orders, you become dependent on more and more geometrical information at this single point. So it is because of this perturbative structure of the calculation that you do not need to make any global assumptions. You just are working locally and just get dependence on these kinds of local objects. But if you want to do something like solve the field equations in the interior of a neutron star, that is something that generically cannot be done analytically and has to be done numerically. So there you have to make some concrete choice for what your target space geometry is. And one toy model we've been working with, which is the same as this U1 model that I was talking about just a while ago, is that we assume that the target space is a sphere, and then we can use stereographic projection, so a two-sphere, and then we use stereographic projection to map that two-sphere to the complex plane. And then that is what we work with in this model of a single complex scalar. And basically, and it actually turns out to be pretty simple. If you work out the kinetic term in that theory of that single complex scalar, that basically represents two real scalars living on a sphere, then you just get a term, you would get just a di mu phi bar, di nu phi, g mu nu term, if you just had a scalar living in the complex plane and no interesting geometry, but you just get a really simple factor, a function of phi bar phi that sits in front of this kinetic term. And it's a really simple function that just depends on the radius of the sphere that you can easily write down. So that is the kind of toy model we are considering as a first step.
Can you not do a field redefinition to absorb this function here?
In the case of a real scalar, yes, but in the case of a complex scalar, no. Yeah, so if phi were real, then absolutely. You can just reabsorb this f into the definition of phi. But if phi is complex, you cannot do it.